Find somewhere comfortable. If you're already in bed, let your body settle a little deeper into whatever is holding you. You don't need to follow any of this closely. You don't need to remember a single word of it. The ideas will arrive on their own, and if some of them drift past you like quiet shapes in the dark, that is perfectly fine. That is, in fact, the whole point. Tonight we're going somewhere vast. We're going to talk about the fabric that holds the universe together, and about the ripples that move through it when the most powerful things in existence collide. Black holes, gravitational waves, the slow, patient machinery of space and time itself. But none of that requires you to sit up or concentrate. It only requires you to rest here, in this room, on this night, and let the words settle around you the way the dart does when you finally stop moving. We are in no hurry. The universe has been doing this for 13 billion years, and it will be doing it long after tonight. So let your breathing slow. Let your thoughts grow a little softer at the edges, and we'll begin. There is something beneath everything. Not beneath in the way a floor is beneath your feet, but beneath in a deeper sense. Something that everything else rests upon, moves through, and is shaped by. Physicists call it spacetime. And understanding what it actually is, not just as a word but as a genuine thing, is where this whole story begins. For most of human history, space was thought of as emptiness, a void, a container, vast, neutral, and unchanging, inside which matter did its business. Stars burned, planets orbited, objects fell, but the container itself just sat there, indifferent and still. Newton's laws of gravity and motion, worked out in the late 17th century, could predict the movements of planets with beautiful precision. They could tell you where Mars would be on a given night 3 centuries from now. They could explain the tides, the arc of a cannonball, the slow wobble of the Earth's axis. For 200 years, this framework was essentially untouched. But Newton himself was quietly troubled by one aspect of his own theory. Gravity, in his description, acted at a distance, instantaneously across any span of space, with no explanation for how. 2 objects on opposite sides of the solar system would somehow feel each other's pull the very moment one of them moved. Newton called this troubling. He wrote, in a letter to a colleague, that the idea of one body acting upon another at a distance, through a vacuum, without any intermediary, was so great an absurdity that he believed no person who had a competent faculty of thinking could ever fall into it. And yet his equations required exactly that. He had no answer. He simply left the mechanism unexplained, and the theory worked so well in practice that most people were content not to ask. Albert Einstein was not content. In 1905, Einstein had already overturned the nature of time and space with his special theory of relativity, showing that neither was the fixed, universal backdrop Newton had assumed, but that both were relative depending on how fast you were moving. Time ran slower for a fast-moving observer, distances compressed. The speed of light was the one constant, and everything else bent around it. These were strange ideas, but they were testable, and they proved correct. Then, for the next 10 years, Einstein worked on something even more ambitious, extending those ideas to include gravity. The result, published in November 1916, was the general theory of relativity, and it changed everything. The central insight of general relativity is this: space and time are not separate things, and they are not a passive container. They are woven together into a single 4-dimensional fabric, space-time, and that fabric is not rigid. It is flexible. It curves and bends in the presence of mass and energy. And what we experience as gravity is not a force at all. It is the geometry of that curved space-time guiding objects along the straightest possible paths through it. The trampoline analogy is the one most people encounter first, and it is genuinely useful, even if it is only a beginning. Imagine a large trampoline stretched tight and flat. Now place a heavy bowling ball at its center. The surface dips. It curves around the ball. If you then roll a marble across the trampoline, it doesn't travel in a straight line. It curves inward, following the contour of the dip. To an observer watching from the side, it looks as though the bowling ball is pulling the marble toward it, but there is no pull. The marble is simply following the curved surface, taking what is, from its own perspective, the most direct path available. In general relativity, massive objects, stars, planets, black holes, do something analogous to that bowling ball, but in 4 dimensions rather than 2, and with time woven in alongside the 3 dimensions of space. The Earth's mass curves the space-time around it, and the Moon follows a path through that curved space-time, a path that loops around the Earth, that appears to us as an orbit, but that is, from the Moon's perspective, the straightest line available through a curved geometry. This distinction matters enormously. In Newton's picture, gravity is a force, something added to the universe, something exerted. In Einstein's picture, gravity is geometry, a property of the stage itself. The stage participates. The stage is not neutral. Every massive object in the universe is constantly reshaping the space-time around it, and every other object moves in response to that reshaping. Now, the trampoline analogy has a limitation that is worth dwelling on for a moment. The trampoline dips downward because of Earth's gravity. It needs an external gravitational field to demonstrate gravity, which is a bit circular. The real curvature of space-time happens in all 4 dimensions simultaneously, including the time dimension, and it is the curvature of time that dominates in most everyday situations. When you drop an apple, it falls not primarily because space is curved, but because time runs at a very slightly different rate, closer to the Earth's surface than it does higher up. Objects naturally drift toward regions where time runs more slowly, and near a massive body, time runs more slowly. This is called gravitational time dilation, and it has been measured with extraordinary precision. Clocks at sea level tick ever so slightly slower than clocks on a mountaintop. The GPS satellites in orbit have to account for this effect in their timing calculations, or the navigation errors would accumulate to kilometers within a single day. Einstein's 1916 paper was not a gentle refinement of Newton. It was a wholesale replacement of the conceptual foundations. Where Newton had an invisible force acting at a distance, Einstein had a dynamic, living geometry. Where Newton's universe was a stage on which events played out, Einstein's universe was itself an actor, responsive, flexible, participant. And here is where the story takes its first quiet turn towards something remarkable. If the fabric of space-time can be bent and warped by mass and energy, then what happens when that mass and energy moves? What happens when it accelerates? When 2 enormous objects circle each other, each bending the space-time around them, each curving the path the other follows, what happens to the fabric between them and beyond them? The answer, which Einstein worked out from his own equations, is that it ripples. A disturbance in the curvature of space-time, caused by accelerating masses, does not stay local. It propagates outward, the way a disturbance in the surface of a pond propagates outward from a dropped stone. It spreads through the universe at the speed of light, carrying with it a tiny rhythmic pattern of stretching and squeezing. Einstein found this result in his own mathematics and was, by some accounts, unsure what to make of it. He went back and forth over the years on whether these waves were physically real or merely a mathematical artifact, a quirk of the coordinate system he was using to describe the geometry. It would take decades, and the work of many others, to settle the question. But the answer, as we now know with certainty, is that the waves are real. They carry real energy. They move through the universe at the speed of light, and they bend the geometry of space as they go. The universe is not a silent, static container. It is a fabric that can ring. To understand what a gravitational wave actually is, it helps to be clear about what it is not. It is not a wave of something moving through space, the way sound is a wave of pressure moving through air, or the way light is a wave of electric and magnetic fields moving through the vacuum. It is a wave that is space, a traveling disturbance in the geometry of space-time itself, a rhythmic change in the very distances between points. Think about what that means for a moment. When a gravitational wave passes through a region, the distances between objects in that region change, not because the objects have moved, they haven't, at least not in the ordinary sense. The space between them has stretched or compressed. The metric, as physicists call it, the measure of distance itself, has fluctuated. And the pattern of that fluctuation is specific and strange. A gravitational wave stretches space in one direction while simultaneously compressing it in the perpendicular direction. Then, half a cycle later, it reverses. The stretched direction compresses and the compressed direction stretches. If you were floating in space and a gravitational wave passed through you, and if the wave were strong enough to feel, you would find yourself alternately elongated top to bottom and squeezed side to side, then squeezed top to bottom and elongated side to side, oscillating back and forth at whatever frequency the wave carried. You would not be shaken in a single direction, the way you might be by a sound wave. You would be gently kneaded in two directions simultaneously in a pattern that physicists call quadrupole, stretching, a squeezing and stretching that always involves two perpendicular axes changing in opposite directions at the same time. Why does this happen? Why do accelerating masses produce this particular kind of disturbance in space-time? The answer lies in the structure of Einstein's equations themselves. General relativity relates the curvature of space-time, the geometry, to the distribution of mass and energy. When that distribution changes, when masses move, accelerate, orbit, nothing in the universe can propagate faster than light. So the information that the mass has moved, the change in the curvature field, spreads outward from the source at the speed of light in the form of a wave. There is a useful analogy in electromagnetism. An electric charge sitting still produces a static electric field around it. If you shake that charge back and forth, the field has to readjust, and that readjustment propagates outward as an electromagnetic wave, light or radio waves, depending on the frequency. Gravitational waves are the gravitational equivalent. A mass sitting still produces a static gravitational field, a curvature of space-time. Shake that mass, accelerate it, and the curvature field has to readjust, and that readjustment propagates outward as a gravitational wave. But there is an important difference. Electromagnetic waves can be produced by a single charge oscillating back and forth, because a single charge has what physicists call a dipole, a separation between positive and negative. Gravitational waves cannot be produced this way, because there is no negative mass. You cannot have a gravitational dipole. The simplest motion that produces gravitational waves is what is called quadrupole motion, a motion that changes the shape of the mass distribution in a way that is more complex than a simple back and forth. Two masses orbiting each other produce exactly this kind of motion. The mass distribution is constantly rotating, constantly changing shape in a way that has that characteristic two-axis symmetry. This is why binary systems, two objects in mutual orbit, are such efficient gravitational wave sources. The mathematical prediction of gravitational waves came from Einstein's 1916 paper, but for decades afterward, the question of whether these waves were physically real or merely a mathematical ghost haunted the field. The equations of general relativity are notoriously complex, and it was genuinely unclear whether the wave solutions represented a real, physical propagation of energy or just an artifact of the way the mathematics was set up. The resolution came, in part, from a beautifully simple thought experiment proposed in 1957 by the physicist Richard Feynman, with refinements from Herman Bondi at a conference in Chapel Hill, North Carolina. Feynman's argument is now called the sticky bead argument, and it goes like this. Imagine a rod with a bead threaded loosely onto it. The bead can slide along the rod, but is held back by friction. It doesn't slide freely, but requires a small force to move it. Now imagine a gravitational wave passing through the rod. As the wave passes, it alternately stretches and compresses the space along the rod's length. The rod itself, being made of atoms held together by electromagnetic forces, resists this stretching and compressing. It tries to maintain its length. But the bead, sitting loosely on the rod, responds to the changing geometry of space and slides back and forth slightly as the wave passes. The friction between the bead and the rod converts this sliding motion into heat. The bead warms up, just slightly. That warming is the key. Heat is real energy. If the bead gains heat, that energy had to come from somewhere. It came from the gravitational wave, which means the gravitational wave was carrying real physical energy, not just a mathematical fluctuation, but something that could do work, warm a bead, and be, in principle, detected. This argument did not constitute a detection, of course. It was a thought experiment, but it settled the conceptual question. Gravitational waves are physically real. They carry energy. They interact with matter, however weakly, and if they interact with matter, even weakly, then a sensitive enough instrument might detect them. But how sensitive would that instrument need to be? This is where the scale of the challenge becomes something that is almost impossible to hold in the mind. The gravitational waves produced by the most violent events in the universe. 2 black holes, each dozens of times the mass of the sun, colliding at a significant fraction of the speed of light. By the time those waves reach Earth, having traveled across 1 billion light-years of space, they distort the geometry of space by an amount that is almost too small to describe meaningfully. The distortion is roughly 1 part in 10 to the power of 21. Written as a fraction, that is 1 divided by a number with 21 zeros after it. To give that a physical meaning, if you stretch the distance from Earth to the nearest star, about 4 light-years, roughly 40 trillion kilometers, a gravitational wave of this strength would change that distance by about the width of a single human hair. Or think of it this way. A single atomic nucleus, the dense core of a single atom, is about 1/10,000th the diameter of the atom itself, which is already invisible to any microscope. A gravitational wave from a merging black hole pair distorts space by less than 1/10,000th of that nuclear width across a 4-kilometer measuring arm. The number is genuinely at the edge of what the human mind can picture. And yet this distortion has been measured. We will come to how. For now, let the scale of it settle somewhere quiet. The universe produces these ripples constantly. Every orbiting pair of stars, every binary neutron star, every pair of black holes slowly spiraling toward each other is radiating gravitational waves right now as you rest here. The fabric of space is faintly trembling with the accumulated motion of billions of massive systems, and the trembling passes through you as you lie here, bending and releasing the space your body occupies by an amount so small it makes the word infinitesimal seem generous. You would never feel it, but the universe is doing it anyway, patient and unhurried, filling the dark with its quiet geometry. Before 2 black holes can collide, they must first exist, and the story of how they come to exist is one of the most extraordinary stories in all of nature. A story of fire and gravity, and the slow exhaustion of something enormous, ending in a collapse so complete that not even light survives it. It begins with a star, not an ordinary star like the sun, but a massive one, perhaps 20, 30, 50, or even 100 times the mass of the sun. These are rare objects, bright blue-white giants that burn through their fuel at a ferocious rate, living fast and dying young by stellar standards. Where the sun will burn steadily for about 10 billion years, a star 40 times its mass might exhaust itself in only a few million. To understand why they collapse the way they do, it helps to understand what holds a star up in the first place. A star is, at its core, a constant negotiation between two opposing forces. Gravity pulls inward, always, relentlessly, with a force proportional to the mass of the star. Every part of the star is being pulled toward every other part, and the whole enormous mass is trying to crush itself into the smallest possible volume. What prevents this is the outward pressure of the nuclear reactions happening in the core. In the heart of a star, hydrogen nuclei are being fused together to form helium, and in that fusion, a tiny amount of mass is converted into a large amount of energy. That energy, radiating outward, creates a pressure that pushes back against gravity. The star exists in a dynamic balance. Gravity compressing inward, radiation pressure pushing outward, the two forces holding each other in equilibrium for millions or billions of years. But the fuel is not infinite. Over time, the hydrogen in the core is consumed. The star begins fusing helium into carbon and oxygen. Then, in more massive stars, carbon fuses into neon and magnesium, neon into oxygen, oxygen into silicon and sulfur, and finally silicon into iron. Each stage produces less energy than the one before. Each stage produces less energy than the one before. The star is burning through progressively heavier fuels with progressively diminishing returns. Iron is the end of the road. Iron fusion does not release energy, it absorbs it. When the core of a massive star becomes iron, there is nothing left to burn. The outward pressure from fusion disappears and gravity wins instantly. What happens next takes less than a second. The core, which might have been the size of the Earth, collapses to a sphere perhaps 20 or 30 kilometers across in a fraction of a second. The outer layers of the star, suddenly unsupported, fall inward behind it. In most cases, the infalling material bounces off the newly compressed core and is blasted outward in a colossal explosion. A supernova, one of the most energetic events in the universe, briefly outshining entire galaxies. But for the most massive stars, something different happens. The core is so massive that even the compressed, incredibly dense matter left behind cannot support itself. In less massive stars, the collapse stops when the core becomes a neutron star, an object perhaps 20 kilometers across, composed almost entirely of neutrons packed together so tightly that a teaspoon of neutron star material would weigh hundreds of millions of tons. Neutron stars are held up by a quantum mechanical effect called degeneracy pressure, a rule arising from the fundamental nature of particles that no two identical fermions can occupy the same quantum state simultaneously. But there is a limit to what degeneracy pressure can hold. This limit, physicists call it the Tolman-Oppenheimer Volkoff limit, though the precise value depends on how matter behaves at extreme densities, lies somewhere around 2 to 3 solar masses for a neutron star core. If the collapsing core exceeds this limit, degeneracy pressure fails. Nothing is left to resist gravity. The collapse continues without stopping. And when nothing stops it, the matter falls inward past a point of no return. That point is called the event horizon. It is not a physical surface. You could, in principle, cross through it without feeling any particular sensation at the moment of crossing. But it is a one-way boundary in space-time, a surface from within which no information, no light, no signal of any kind can ever escape. The escape velocity, The speed you would need to reach to escape the gravitational pull exceeds the speed of light, and since nothing can travel faster than light, nothing can escape. Everything that falls inside is lost to the outside universe forever. What remains from the outside is a region of space defined by that boundary, the event horizon, surrounding a gravitational field of extraordinary intensity. This is a black hole. The matter that collapsed to form it is, in our best current understanding, compressed into a singularity at the center, a point of infinite density where the known laws of physics break down. The singularity itself may be a signal that our theories are incomplete, that some future understanding of gravity at the quantum scale will replace the singularity with something more physically meaningful. But the event horizon and the region of no return it defines is real and well described by general relativity. The black holes involved in the first detected gravitational wave event, the one designated GW50914, had masses of approximately 29 and 36 times the mass of the Sun. To form black holes of this size, the original stars would have been substantially more massive still, perhaps 60 to 80 solar masses each, with much of that mass blown away in stellar winds and the supernova explosion itself. These were enormous, ancient stars, formed when the universe was younger and the conditions for making such giants were more common. Now picture those two black holes, 36 solar masses, 29 solar masses. The mass of the Sun is about 2 million trillion kilograms, a number that genuinely resists imagination. Multiply that by 36 or by 29. And then compress all of that mass into a region of space smaller than a city. The 36 solar mass black hole in GW50914 had an event horizon with a radius of roughly 106 kilometers, smaller than the distance from one end of a large city to the other, yet enclosing the equivalent mass of 36 suns. The density implied by this is extraordinary. Not the density of the singularity, which may be infinite, but the average density within the event horizon, the mass divided by the volume enclosed. For a black hole of this size, that average density is actually comparable to the density of an atomic nucleus. For smaller black holes, the density within the event horizon is higher still. For supermassive black holes, billions of times the mass of the Sun, the average density within the event horizon can be surprisingly modest, less than the density of water. Size and density trade off in ways that are counterintuitive. But how did two black holes come to be orbiting each other? The most likely answer is that they were born that way, as a binary star system. Two massive stars born from the same cloud of gas, orbiting each other from the beginning. Binary star systems are common. Roughly half of all stars in the galaxy are in binary or multiple systems, born together from the same collapsing gas cloud, orbiting a common center of mass. If both stars in such a system are massive enough, they will each eventually exhaust their fuel, each collapse, each form a black hole, and the two black holes will inherit the orbit that the two stars had before them. The orbit at that point might be very wide, the two objects separated by a substantial fraction of a light year, taking thousands of years to complete a single revolution. They would be locked together by their mutual gravity, each curving the space-time the other moves through, each tracing a path through the geometry the other creates. But not permanent, because every orbit radiates, and that radiation, over time, draws them closer. Imagine two black holes, separated by a distance that would take light several hours to cross, orbiting each other in the slow, stately way that planets orbit stars. Each revolution takes years, perhaps centuries. From the outside, they might seem almost frozen, two dark, city-sized regions of no return, circling each other across an immensity of space, with nothing in between them but the curved geometry their masses create. But something is happening quietly and constantly that will eventually bring them together. they are losing energy. With every single orbit, they radiate a tiny amount of that energy away as gravitational waves, and the orbit shrinks, just slightly in response. The mechanism is worth following carefully, because it is a beautiful and somewhat counterintuitive piece of physics. When a gravitational wave carries energy away from the system, the total energy of the two black hole system decreases. Now, in orbital mechanics, a lower energy orbit is actually a smaller, faster orbit, not a larger, slower one, which might be your first instinct. This is because the gravitational potential energy and the kinetic energy of an orbit are linked in a specific way. As an object falls to a lower orbit, it moves faster, and the gain in kinetic energy is only half the loss in potential energy, with the other half radiated away. So losing energy to gravitational waves means the orbit shrinks, and a smaller orbit means the objects move faster. Faster motion means more energetic, more rapidly changing gravitational fields. More energetic, more rapidly changing fields mean more gravitational wave emission, which means more energy loss, a smaller orbit still, faster motion, even more emission. The process is self-reinforcing. It starts imperceptibly slowly and accelerates over vast timescales, ending in a rush. For a binary system like the one that produced GW50914, this in spiral, the slow, self-accelerating spiral inward, took something on the order of 1 billion years or more. 1 billion years of gradually tightening orbits, each revolution slightly shorter than the last, the gravitational wave emission growing incrementally stronger with each passing millennium. For most of that time, the waves would have been at extremely low frequencies, completing only a tiny fraction of a cycle per second, far below anything our current instruments could detect. The first strong evidence that this process was real, that binary systems genuinely radiate gravitational waves and shrink their orbits in precisely the way general relativity predicts, came not from black holes, but from neutron stars, and not from a direct detection, but from an indirect measurement of extraordinary precision. In 1974, two astronomers at the Arecibo Radio Telescope in Puerto Rico, Russell Hulse, then a graduate student, and his supervisor Joseph Taylor, discovered something remarkable. While conducting a systematic survey of pulsars, Hulse found a pulsar that was behaving strangely. A pulsar is a neutron star that emits a narrow beam of radio waves from its magnetic poles. As it rotates, that beam sweeps around like a lighthouse beam, and if Earth lies in the path, we receive regular pulses of radio energy. Ticks, almost, of extraordinary regularity. Pulsars are among the most precise clocks in nature. This particular pulsar, designated PSR B1930+16, was showing a systematic variation in the timing of its pulses. Sometimes they arrived slightly early, sometimes slightly late, in a regular pattern that repeated every 7 hours and 45 minutes. Hulse recognized this pattern. The pulsar was in a binary system orbiting another star, and the variation in pulse timing was due to the Doppler effect. The pulsar moving toward Earth and then away from Earth as it orbited, shifting the frequency of its radio pulses slightly, just as the pitch of a passing siren shifts as it moves toward and then away from you. The companion star turned out to be another neutron star, not a pulsar, so invisible in radio, but detectable through its gravitational influence on the pulsar. Here was a binary system of two neutron stars, each about 1.5 solar masses, orbiting each other at close range with a period of under 8 hours. General relativity predicted that such a system should be radiating gravitational waves and losing energy, causing the orbit to shrink, causing the orbital period to decrease by a tiny but measurable amount each year. Taylor and his colleagues measured the orbital period over years, then decades. The orbit was shrinking, the period was decreasing, and the rate of decrease matched the prediction of general relativity to within a fraction of a percent, with no adjustable parameters, no fudge factors, just the clean prediction of the theory applied to the measured masses and orbital parameters of the system. This was the first indirect evidence that gravitational waves were real, not detected, but inferred from their effect. The energy was going somewhere, and the only somewhere consistent with the mathematics was into gravitational waves. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery, and it stands as one of the most precise confirmations of any physical theory in the history of science. But back to our two black holes. After 1 billion years of in-spiral, the orbit has shrunk to something human scale in comparison to its beginning. The two objects now separated by perhaps a few hundred kilometers, completing hundreds of orbits per second, moving at a substantial fraction of the speed of light. The gravitational wave emission is now enormous. The waves are sweeping through the audio frequency range, starting below what a human ear could hear, climbing rapidly upward through tens of cycles per second, through 100 toward 200 as the objects close in. The final moments of GWN FIFO 914's in-spiral lasted a fraction of a second. In the last few orbits before merger, the two black holes were completing full revolutions in milliseconds, separated by a distance smaller than the radius of the Sun, their event horizons about to touch. They were moving at roughly 60% of the speed of light. The gravitational wave signal they were emitting was climbing rapidly in both frequency and amplitude, a pattern that physicists and audio engineers who have since converted the signal to sound call a chirp. It starts low and quiet, rises in pitch and volume, and then reaches a peak at the moment of merger. Think of what it means for something 36 times the mass of the Sun to be moving at 60% of the speed of light. The Sun, recall, is about 1.5 million kilometers across. Its mass is almost 2 million trillion kilograms. 36 of those compressed into a sphere a couple of 100 kilometers across, hurtling through space at nearly 200,000 kilometers per second. The numbers describe something so far outside ordinary experience that they can only be held lightly, turned over slowly, like a smooth stone in a quiet hand. And that is only one of the 29 solar masses beside it, both curving space-time so severely that the geometry between them is twisted and churning, the gravitational wave emission in those final milliseconds pouring out energy at a rate that briefly exceeded the combined light output of every star in the observable universe. The long patience of 1 billion years compressed into a fraction of a second. To detect the distortion that a gravitational wave makes as it passes through Earth requires an instrument of a kind that had never existed before in human history, something capable of measuring a change in length smaller than 1/10,000th of the diameter of a single proton across a distance of 4 kilometers. Not approximately that sensitive. Exactly that sensitive. The physics does not offer more signal than that, and so the instrument must be capable of finding it. The principle behind the instrument is called laser interferometry, and it is worth understanding in some detail, because the elegance of the idea is part of what makes the achievement so remarkable. Light, as you may recall from school, is a wave. It has peaks and troughs, and when two beams of light meet, they can interfere with each other, the peaks of one adding to the peaks of the other to make a brighter region, or the peaks of one meeting the troughs of the other and cancelling out, making darkness. This interference pattern is exquisitely sensitive to the relative lengths of the paths the two beams have traveled. If one beam's path is even a tiny fraction of a wavelength longer than the other's, the interference pattern shifts noticeably. LIGO, the Laser Interferometer Gravitational Wave Observatory, exploits this sensitivity. A single laser beam is split into two beams by a partially reflective mirror called a beam splitter, placed at the intersection of two long tunnels, each 4 kilometers in length, arranged in an L shape. One beam travels down one arm of the L, the other travels down the perpendicular arm. At the far end of each arm, a mirror reflects the beam back. The two beams return to the beam splitter and recombine. The system is tuned so that, in the absence of any disturbance, the two returning beams cancel each other out almost perfectly, their peaks and troughs aligned in opposition, producing what is called destructive interference. Now, a gravitational wave arrives. As it passes through the detector, it stretches one 4-kilometer arm and compresses the other, that characteristic quadrupole pattern. The two arms are no longer the same length. One beam has traveled a slightly longer path than the other. When they recombine, they no longer cancel perfectly. A faint pattern of light appears at the detector. That faint pattern, its brightness varying as the wave oscillates, is the signal. The change in arm length that LIGO must detect is approximately 10 to the power of negative 19 meters, that is, roughly 1/10,000th of the width of a proton. A proton is itself about 1 femtometer across, which is 1/1,000,000th of a billionth of a meter, 1/10,000th of that, across 4 kilometers. The precision required is, by any ordinary standard, not merely extraordinary, but absurd. How is it achieved? The first requirement is light that is extremely coherent, laser light, with all its waves in lockstep, so that tiny path length differences produce measurable interference shifts rather than being washed out by random variation. LIGO uses a laser of very high power, and the light is bounced back and forth between the mirrors in each arm hundreds of times before being recombined, effectively turning each 4-kilometer arm into a path of hundreds of kilometers. This amplifies the sensitivity proportionally. The mirrors themselves are among the most perfect objects ever manufactured. Each one is a disc of glass about 34 centimeters across, polished to a surface smoothness measured in atoms, coated with layers of materials designed to reflect light with extraordinary efficiency. They hang from glass fibers, suspended in a multi-stage vibration isolation system, a cascade of pendulums, each one reducing the transmission of vibration from the ground to the mirror by a factor of many thousands. The whole assembly sits inside an ultra-high vacuum system, because even the random thermal motion of air molecules would create enough noise to drown the signal entirely. Then there is the problem of seismic noise. The Earth is never truly still. Distant earthquakes, ocean waves breaking on coastlines thousands of kilometers away, traffic on roads, the footsteps of people in nearby buildings. All of these create vibrations in the ground that would, without isolation, overwhelm any gravitational wave signal. LIGO's seismic isolation system is a marvel of engineering in its own right. A series of active and passive vibration-cancelling platforms, each stage reducing the transmitted motion, so that by the time a vibration reaches the mirror, it has been attenuated by a factor of roughly 10 billion compared to the ground motion. Even quantum mechanics poses a problem. At the sensitivity LIGO requires, the quantum nature of light itself becomes a source of noise. Individual photons arrive at the detector randomly, and this randomness, called shot noise, creates a fundamental limit on how precisely the interference pattern can be measured. LIGO uses a technique involving what are called squeezed light states, a method of manipulating the quantum uncertainty of the light so that the uncertainty in one measurable property is reduced at the cost of increasing uncertainty in another, less relevant property. This is a quantum optical trick that requires careful engineering but pushes the sensitivity beyond what would otherwise be achievable. The conceptual origins of the interferometric approach go back to the late 1960s, when a physicist named Rainer Weiss, working at the Massachusetts Institute of Technology, began thinking about how one might detect gravitational waves with lasers. He worked out, in a 1972 technical report that became something of a founding document for the field, a detailed analysis of the noise sources that would need to be overcome and how they might be overcome. His analysis was extraordinarily prescient. Essentially everything he identified as a challenge in 1972 was indeed a challenge that had to be solved before LIGO could work. The project grew through the 1980s and 1990s into a large collaboration involving thousands of scientists and engineers across dozens of institutions. Barry Barish joined as director in 1994 and is widely credited with transforming LIGO from a promising but somewhat chaotic research project into a disciplined, large-scale scientific enterprise, restructuring the collaboration, securing the funding, and overseeing the construction of the two detectors. Two detectors, because a single instrument cannot distinguish a genuine gravitational wave signal from local noise. You need two geographically separated instruments, and a real signal must arrive at both, with a time delay consistent with the speed of light traveling between them. LIGO has two sites, one in Livingston, Louisiana, set among pine forests in the flat lowlands, and one in Hanford, Washington, in the high desert of the Columbia River Plateau. They are roughly 3,000 kilometers apart. A gravitational wave arriving from a particular direction in the sky will reach one detector before the other, with a delay of up to 10 milliseconds depending on the direction. A signal appearing at both detectors within that time window, with consistent shape and amplitude, is a gravitational wave candidate. On the morning of September 14, 2015, at 5:51 in the morning Central Time, a signal arrived at the Livingston detector. 7 milliseconds later, the same signal arrived at Hanford. It was the first gravitational wave ever directly detected by humanity. And neither detector had been formally operating for very long. LIGO had just completed a major upgrade and was in what engineers call an engineering run, a period of testing and calibration before the official science run began. The universe, apparently, did not wait for the formal opening. There is a particular quality to the morning of a discovery. The people involved rarely know, in the moment, that they are living through something that will be written about for centuries. They are tired, perhaps. They are checking instruments. They are doing the ordinary work of science, which is mostly careful, repetitive, and unglamorous. And then something happens that is not ordinary at all. On September 14, 2015, the data coming from LIGO's two detectors contained a signal. It appeared first at Livingston, Louisiana, then 7 milliseconds later at Hanford, Washington. The raw data, when plotted as a graph of the detector's strain, the fractional change in arm length against time, showed a gentle oscillation that grew in amplitude and frequency over about 0.2 of a second, reached a peak, and then faded rapidly. The shape was a chirp. A rising, quickening wave, climbing in frequency like a sound rising in pitch, then cutting off. The signal matched, with extraordinary precision, the theoretical prediction for the merger of two black holes. Not approximately, not suggestively, with a precision that left essentially no room for alternative explanations. What the signal was encoding, in its shape and timing and amplitude, was the complete story of a merger that had occurred 1.3 billion light-years away. The two black holes involved had masses of approximately 36 and 29 times the mass of the Sun. They had been spiraling inward for perhaps 1 billion years or more. In the final fractions of a second captured by LIGO's instruments, they were completing their last few orbits, whipping around each other at a substantial fraction of the speed of light. At the moment of merger, the two event horizons touched and the two black holes became one. The resulting single object had a mass of approximately 62 solar masses. But wait, 36 plus 29 is 65, not 62. 3 solar masses are missing. Those 3 solar masses were converted, in that fraction of a second, entirely into gravitational wave energy. 3 times the mass of the Sun, converted completely to energy, released in a fraction of a second. To appreciate what that means, consider that the Sun converts mass into energy through nuclear fusion at a rate that powers the entire solar system, and over its entire 10 billion year lifetime, the Sun will convert about 0.1% of its mass to energy in this way. In the GW5914 merger, 3 entire solar masses, 3,000 times what the Sun will convert in its whole existence, were released in the time it takes to blink. The peak power output of GW150914 at the moment of merger was roughly 3.6 times 10 to the power of 49 watts. For comparison, the total luminosity of the observable universe, all the light from all the stars in all the roughly 2 trillion galaxies we can see, is estimated at around 5 times 10 to the power of 42 watts. The GW50914 merger was, for that brief fraction of a second, emitting gravitational wave energy at a rate about 10,000 times greater than the combined light output of the entire observable universe. And yet the waves that arrived at Earth, having travelled 1.3 billion light-years, caused a distortion in LIGO's 4-kilometre arms of about 4,000ths of a proton width. The signal was genuine. The universe is vast, and it dilutes even the most prodigious outputs across unimaginable distances. After the merger, the newly formed black hole did not immediately settle into a quiet, spherical state. It was distorted, asymmetric, wobbling, its event horizon ringing like a struck bell. This ringing, called ringdown, also carries gravitational waves at a characteristic frequency determined by the mass and spin of the new black hole. The ringdown signal in GW10914 faded within a few milliseconds as the black hole shed its asymmetry and settled into its final, stable configuration. The team at LIGO did not immediately announce what they had found. The initial signal was noticed almost at once by automated analysis software, and within hours, physicists were looking at the data. But science requires verification, and this was not an ordinary claim. The first detection of gravitational waves, confirming a century-old prediction of general relativity, confirming the existence of binary black hole systems of this mass, and inaugurating an entirely new field of astronomy. This required months of careful analysis. There was also the question of whether the signal could be an injected test. LIGO has a practice of occasionally inserting fake signals into the data stream without telling most of the collaboration, blind injections designed to test whether the analysis pipelines work correctly and whether the team's response is appropriate. The first question that had to be answered was whether September 14 was a blind injection. It was not. The injection team confirmed this relatively quickly. The signal was real. The collaboration spent 5 months checking and rechecking. They modeled the noise properties of the detectors exhaustively. They ran the signal through multiple independent analysis pipelines. They calculated the probability that random noise could have produced a signal of this shape and strength at both detectors within 7 milliseconds of each other. That probability was vanishingly small. The signal was estimated to be more than 5 standard deviations above the noise floor, which in physics means a false alarm. Probability of less than 1 in several million. On February 11, 2016, at a press conference held simultaneously in Washington and at research institutions around the world, the LIGO Scientific Collaboration and the Virgo Collaboration announced the detection. The phrase, "We did it," appeared in many of the scientists' private messages to each other in the moments before the public statement. There is a strange and rather beautiful footnote to all of this. Albert Einstein, who worked out the mathematics of gravitational waves in 1906, spent much of the rest of his life doubting they could ever be detected. In a 1936 paper written with Nathan Rosen, he actually argued that gravitational waves did not exist, though an error in the calculation was later found by a referee and the paper was revised before publication. Einstein died in 1955, 60 years before the detection that confirmed his most profound prediction. And the signal itself, when translated into sound, when the rising frequency and amplitude of the chirp are mapped into the audio range human ears can hear, lasts about 0.2 of a second. It sounds like a soft rising whoop. A brief, gentle sound. The kind of thing you might almost miss if you were not listening carefully. It carried information about an event that happened 1.3 billion years ago, when the most complex life on Earth was still single-celled, when the continents were arranged in configurations no human eye has ever seen. The universe had been carrying that information across the void for longer than animals have existed on this planet, and it arrived on a September morning in the pine forests of Louisiana and the high desert of Washington in the form of a quiet, rising chirp. The detection of GW 50914 was not an ending. It was the opening of a door. And through that door, in the years since, has come a flood of signals, each one carrying information about events the universe had kept hidden until now. By the time of LIGO's fourth observing run, well into the 2020s, the catalogue of gravitational wave detections had grown to over 300 events. 300. Each one a merger, a collision, a catastrophic event billions of light years away, each one encoding in its shape and timing and amplitude a detailed record of the masses involved, the distances, the spins of the objects, the geometry of the collision. The universe had been doing this all along. We simply had not been listening. But among those hundreds of detections, a few stand out for what they revealed about the physics of the cosmos. In August 2017, LIGO and its European partner detector Virgo, based in the Tuscan countryside near Pisa, Italy, detected a signal unlike any seen before. The signal was longer, lasting over 100 seconds, and its character was different from the black hole mergers that had preceded it. Analysis showed it was produced not by two black holes, but by two neutron stars, each about 1.5 solar masses, each roughly the size of a city, made of matter so dense that its internal physics remains one of the deepest open questions in astrophysics. This event, designated GW 70817, was also detected by a network of gamma-ray telescopes in space, just 1.7 seconds after the gravitational wave signal ended. The gamma rays arrived almost simultaneously with the gravitational waves, confirming that gravitational waves travel at exactly the speed of light, not merely approximately. This was a crucial test of general relativity, and it passed with flying colors. What followed over the next days and weeks was unprecedented in the history of astronomy. Telescopes around the world and in space trained their attention on the region of sky from which the signal had come. A galaxy called NGC 4993, about 130 million light-years away in the constellation Hydra. They watched as the merger site glowed and then faded through a sequence of colors, from blue-white to red, over the course of about 2 weeks. This fading glow, called a kilonova, was powered by the radioactive decay of heavy elements freshly forged in the collision. And here is something worth holding for a moment. The gold in a ring, the platinum in a catalyst, the iodine in your body, the strontium in fireworks. These elements, the ones heavier than iron that cannot be made in ordinary stellar fusion, have to be made somewhere. For decades, the leading candidates were neutron star mergers, but this was theoretical. GW 70817 provided the first direct observational evidence. The kilonova spectrum showed the signatures of these heavy elements being created in real time in the debris of two colliding neutron stars. The gold in the world did not come from stars burning quietly in the night. It came from catastrophes like this one, from two neutron stars, patient and ancient, finally drawn together after millions of years, releasing in their collision the material that would eventually find its way into oceans, into rocks, into living things, into the hands of people who would never know where it came from. In May 2019, LIGO and Virgo detected an event called GW 190521. It was brief, only about 1/10 of a second, and the two objects involved were extraordinary. One had a mass of about 85 solar masses, the other about 66. The merger produced a black hole of roughly 142 solar masses. This was significant for a reason that requires a small detour into stellar physics. Black holes in the mass range from roughly 65 to about 135 solar masses are thought to be difficult or impossible to form directly from stellar collapse because stars in the right mass range are believed to undergo a process called pair instability, a sequence of events driven by the creation of electron-positron pairs deep in the stellar core that causes the star to explode completely without leaving a remnant. This creates a gap, sometimes called the pair instability mass gap, in the expected distribution of black hole masses. Both of the black holes in GW190521 appear to fall within or near this gap. This was not expected. It suggests that these black holes may have formed through previous mergers, black holes that were themselves the products of earlier collisions, or through some other mechanism not yet fully understood. The universe, apparently, finds ways to fill in gaps that theory declares should be empty. The analysis of GW190521 also produced a remarkable result from researchers at the Max Planck Institute for Gravitational Physics in Hanover, published in late 2023. They found strong evidence that the black hole formed by the merger rang at not one but two distinct frequencies simultaneously during its ring-down phase. The dominant frequency was 63 cycles per second. The second was 98 cycles per second. Each had its own damping time. The 63 cycle tone fading over about 26 milliseconds, the 98 cycle tone over about 30 milliseconds. This is called black hole spectroscopy, the study of the tones a black hole rings at after it forms, in the same way a bell rings at multiple harmonics simultaneously. General relativity makes a specific prediction, sometimes called the no-hair theorem, a memorable name for the idea that a black hole, once it has settled, is completely described by just three properties: its mass, its spin, and its electric charge. If the no-hair theorem holds, then the frequencies and damping times of all the ring-down tones must be consistent with those three properties. The observation of two simultaneous tones in GW190521 allowed a test of this prediction. No violations were found. The black hole rang exactly as general relativity said it should. Then, in 2003, something else happened. Something that opened an entirely new window on the gravitational universe at frequencies far lower than anything LIGO can detect. Several large scientific collaborations, working independently in North America, Europe, Australia, and China, announced evidence for a gravitational wave background pervading the cosmos. These collaborations use an entirely different detection method from LIGO, one involving pulsars, those extraordinarily regular rotating neutron stars that tick like cosmic clocks. The method is called pulsar timing, and the principle is this: if a low-frequency gravitational wave is passing through the galaxy, it will very slightly stretch and compress the distances between Earth and various pulsars, causing the pulses from those pulsars to arrive fractionally early or late. By monitoring dozens of pulsars simultaneously over many years and looking for correlated variations in their timing that match the expected pattern of a gravitational wave background, these pulsar timing arrays can detect gravitational waves with frequencies in the nanohertz range, billionths of a cycle per second, corresponding to waves with periods of years to decades. The 2023 announcements from the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array all found consistent evidence for this background signal. The most likely explanation is a population of supermassive black holes, objects millions or billions of times the mass of the Sun, lurking at the centers of distant galaxies, slowly spiraling toward each other and emitting gravitational waves at these extremely low frequencies. The background is a kind of gravitational hum, the accumulated murmur of countless such mergers across cosmic history. We now have two entirely separate windows onto the gravitational universe. One, opened by LIGO and its partners, sees the high-frequency end, the sharp, brief chirps of stellar mass black holes and neutron stars merging over fractions of a second. The other, opened by pulsar timing arrays, hears the deep, slow rumble of supermassive black holes taking millions of years to complete each orbit. Between them, they span a range of frequencies as wide as the difference between a deep bass note and a bat's ultrasonic cry. Everything we have talked about tonight, the merging black holes, the rippling space-time, the exquisite instruments, the catalogue of detections, all of it concerns events that happened within the last few billion years of a universe that is nearly 14 billion years old. The signals we have detected so far are, in a cosmic sense, recent history. They are news from the middle period of the universe's life. But gravitational waves carry a promise that goes deeper than this. They carry the possibility of reaching back to the very beginning, to the first moments after the Big Bang, to a time so early and so extreme that no other form of observation can penetrate it. Here is why. The universe we observe with telescopes is a universe of light. Almost everything we know about the cosmos beyond our solar system comes from electromagnetic radiation, visible light, radio waves, infrared, X-rays, gamma rays, all of which are different frequencies of the same fundamental phenomenon. And the universe is, on the whole, transparent to light. Photons can travel vast distances without being absorbed, which is why we can see galaxies billions of light years away. But the early universe was not transparent. In the first few 100,000 years after the Big Bang, the universe was so hot and so dense that it was a plasma, a seething, opaque soup of free electrons and atomic nuclei through which light could not travel freely. Photons were constantly absorbed and re-emitted, scattered and redirected, unable to move more than a tiny distance before being caught again. The universe was, in this sense, a fog. At around 380,000 years after the Big Bang, a moment that sounds long but is a tiny fraction of the universe's current age, the universe had expanded and cooled enough that electrons and nuclei could combine into neutral atoms. The fog cleared. Photons were suddenly free to travel, and they have been traveling ever since. We detect this ancient light today as the cosmic microwave background, a faint glow of microwave radiation arriving from all directions, carrying a snapshot of the universe as it was at that moment of clearing. The cosmic microwave background is the oldest light in the universe, and it is, in a deep sense, a wall. No electromagnetic signal can reach us from before that moment of clearing, because before that moment, the universe did not allow light to travel freely. Everything that happened in the first 380,000 years, the formation of the first atomic nuclei, the processes that set the initial conditions for all subsequent structure, the physics of the very early universe, is hidden behind this wall of light. Gravitational waves are not hidden. They interact with matter so weakly that they pass through virtually everything without being absorbed. A gravitational wave produced in the first fraction of a second after the Big Bang would travel through the plasma of the early universe without being scattered, without being absorbed, without being deflected. It would arrive at our detectors today carrying information from that earliest, otherwise inaccessible epoch. This is the deep promise of gravitational wave astronomy, that it is, in principle, the only messenger that can reach us from the universe's infancy. What might we find there? Several possibilities are considered seriously by physicists, though none has yet been detected. One possibility involves what are called phase transitions in the early universe. In the first tiny fractions of a second after the Big Bang, the universe went through a series of rapid changes in its fundamental properties, transitions somewhat analogous to water freezing into ice, where the symmetry of the system changes abruptly. These transitions could have produced gravitational waves, and the character of those waves would carry information about the physics involved, about the forces of nature as they existed at energies far beyond anything accessible to particle accelerators. Another possibility involves cosmic strings. These are hypothetical objects, not strings in the sense of thread, but one-dimensional defects in the fabric of spacetime, enormously thin but enormously long, stretched across cosmological distances, vibrating and intersecting and occasionally snapping. If they exist, they would produce gravitational waves with a distinctive signature. Their existence is predicted by some theories of fundamental physics, but they have not been confirmed. A third, and perhaps the most profound possibility, involves the signature of inflation. In the very earliest moments of the Big Bang, within the first tiny fraction of a second, the universe is thought to have undergone a period of extraordinarily rapid expansion, called inflation, during which it grew from a microscopic to a macroscopic scale in an almost incomprehensibly brief time. Inflation is supported by strong, indirect evidence. It explains the large-scale uniformity of the cosmic microwave background, among other things, but it has not been directly confirmed. If inflation occurred, it would have produced gravitational waves, and the imprint of those waves might be detectable in the polarization of the cosmic microwave background, or eventually in direct gravitational wave measurements. These are not certainties. They are possibilities, things the universe might be telling us if we can build instruments sensitive enough to hear. The next major step toward that sensitivity is LISA, the Laser Interferometer Space Antenna. LISA is a mission planned by the European Space Agency with contributions from NASA designed to detect gravitational waves from space rather than from the ground. It consists of 3 spacecraft, each separated from the others by about 2.5 million kilometers, forming an equilateral triangle in space, trailing Earth in its orbit around the Sun. The principle is the same as LIGO's, laser beams sent between the spacecraft, measuring the changing distances between them as gravitational waves pass. But the scale is incomparably larger. Where LIGO's arms are 4 kilometers long, LISA's will be 2.5 million kilometers long. This enormous baseline makes LISA sensitive to gravitational waves at much lower frequencies than LIGO can detect. The frequency range that includes the mergers of supermassive black holes, the inspiral of compact objects into galactic center black holes over thousands of orbits, and potentially the primordial gravitational wave background from the early universe. LISA is currently scheduled for launch in the mid-2030s. When it begins operating, it will open yet another window, a low-frequency window in space, complementing LIGO's high-frequency ground-based window and the pulsar timing array's nanohertz window. Together, these 3 approaches will give humanity a view of the gravitational universe, spanning an enormous range of frequencies and timescales. From the deep, slow hum of supermassive black hole pairs to the brief, sharp chirps of stellar mergers to, perhaps eventually, the faint primordial murmur from the universe's very first moments. And there is something quietly wonderful about this, something worth sitting with as you rest here in the dark. The universe began in a state we cannot see, with light that cannot reach us. For most of human history, and for all of the history of astronomy before the last decade, the early universe was simply inaccessible, a sealed room. But the universe left another kind of record. It left ripples in space-time itself, and those ripples have been traveling since the beginning, passing through everything, slowing for nothing, carrying their ancient information through billions of years of cosmic history. We are, right now, in the earliest days of learning to read that record. We have detected a few hundred signals from the middle period of the universe's life. We have heard the first hints of a background hum from supermassive black holes. We are building the instruments that may, in the coming decades, reach back to the universe's infancy. It is a slow process. It takes years to build a detector, Years to accumulate data, years to analyze it, years to understand what it means. The universe is patient, and perhaps that is appropriate. It has been sending these signals for billions of years, and it will continue sending them for billions more. There is something in that which feels, if you let it, rather comforting. The universe is not waiting for us to catch up. It is simply continuing, as it always has. Expanding, evolving, its black holes circling and merging, its neutron stars forging gold in their collisions, its space-time rippling with the accumulated motion of everything that has ever moved. They have been passing through this planet since before the first fish swam in the first ocean. They will be passing through whatever remains of this world long after the last light goes out. And we, for a brief and astonishing moment in the middle of all of that, have learned to listen. The room is quiet. The day is already somewhere behind you, growing distant. The universe hums its ancient gentle frequencies through the dark, through the walls, through you, and out the other side, carrying its patient information onward into the vast and unhurried deep. Drift now, if you are ready. You have heard enough for one night. Sleep well.